Here's just a quick distributed load problem example. So what we have here is a beam and a distributed load on top, and we want to know the magnitude and location of the resultant of the distributed load. Okay, so the resultant what it's talking about is this over here. So we're going to go from a distributed load to two concentrated loads and then add those together to a single distributed load and the reactions at the beam support. So this is a fixed support. That means it's going to be fighting back with a force and a moment. Okay, looking at this, there's no loads in the x direction. There's no wind blowing or anything. Everything is in the y direction. To get the force in the y direction, we're going to split this guy into shapes, kind of like finding the centroid of something. Let's split it into a triangle and a rectangle. And for the rectangle, this green area, that's going to be 400 newtons per meter for the load curve, but we don't want newtons per meter, we want newtons. So what we're going to do is it's the area of this rectangle is our load. So the height, 400 newton per meter, times the base, just base times height is area. So 400 times 6, that's going to get us the force. And just look at your units to be sure of what you're doing. So newtons per meter times meter equals newtons. So there's the force from our green rectangle. And the center of this green rectangle, that's where the force is acting, is going to be over at 3 meters. Okay, let's try out the triangle. So the triangle, we're not going to use the entire 1600 newton per meter because we're not going all the way to the bottom. We just want the height of this chunk. So this is going to be equal to 1600 minus 400. So just the blue part, not the green part. And what's the area of a triangle? Well, that's just 1/2 base times height, so equals 0.5 times the base is 6 meters and times the height is this 1200. And the position on the triangle that this load is going to act, it's just like the centroid. It's 1/3 from the base or 2/3 from the end. So 2/3 of 6, that's going to be 4 meters. And so for the resultant force for the magnitude, all we're going to do is just add together these two components. And so there's this one. Let's see. This plus this. Okay, so there's the magnitude. We also need to know the location of this guy. Okay, so how would we get the location? That's going to be a moment calculation, right? We need to know what distance it's at. And it's probably going to be somewhere in between 3 meters and 4 meters, right? A little bit past the halfway point. Okay, so to get the position, it is a moment calculation. So from A, we're going to find the moment around A and get the equivalent position for this green rectangle. So from A to where the force is applied, that's going to be 3 meters. And for the blue triangle, that's going to be 4 meters. So let's just pop through. It's always safer to make the whole cross product. And for both of these, the force is in the negative y direction. It's going straight down. Now, there's what the force is doing, and there's the reaction of it against the wall. Okay, so here's the moment. The moment's going to be in the k direction. Just a bunch of zeros everywhere else. So R cross F, and then the overall moment, we're going to add each of these together. Okay, so if that's the moment around A is going to have to be opposite of the moment created by the force. So use your right-hand rule, and hopefully you can see that the moment around A would be positive, while the force creates a negative moment. And what the force is creating versus what A is reacting with, those two are going to add up to 0 for static equilibrium. And we also want the distance for this equivalent load. Okay, so this moment is equal to the force times the distance. Okay, so let me just make a quick little table here. So our equivalent force is this guy right here, and that would mean our distance is equal to the moment divided by our force. 3.6 meters. So that makes sense, right? It's right between 3 and 4. So here's our distance. It's going to be 3.6 meters. The force in the y direction is 6,000 newtons, and the moment around A is 21,600 Newton times meters. The moment is always larger than the force because the moment isn't just a force, it's R cross F. So the moment is always larger, and if something's going to fail, typically it's not a force that's going to break it, it's the moment that's going to break it because the moment it's just always larger. It's multiplied by something. Okay, hope that helped you.